Greetings and welcome to the New Calculus Game. My name is John Sylvester. Now, before I get into today's content, I wanted to mention that in my last video yesterday, I got a few comments from some of the people in the New Calculus community that my accent and understanding of my microphone is not great. I apologize for that. I will try to speak clearly today. But today, let's get into the maths. I have a very interesting theorem for you, or equation rather, and I thought it'd be interesting to present the bullshit mainstream mathematical version first, and then show you the true John Gabriel proof of this using the new calculus. Or in the literature called Euler-Lagrange equation. I think because none of them really proved it because they're using the fake numbers. I think we call them the John Gabriel equations. And basically, I'm going to first present the proof in the mainstream calculus, and then we're going to go over it and show why it's wrong and do it correctly in the new calculus, okay? So be prepared for the first bit of this video for a bunch of bullshit, ill-formed mathematician concepts, and then we're gonna convert it to the correct version. And this is gonna be pretty useful for you if you're trying to learn the new calculus, because a lot of maths is written in the short of academia version, so it's pretty nice to know how on the fly between it and the new calculus. So, without further ado, let's begin with the Euler-Lagrange or the John Gabriel equations. So, we have this function right here, and I'm going to call it capital Fy, and it's going to be the integral from alpha to beta of f of x, y prime dx. And this fx, y prime here, this is like essentially, essentially we're inputting a function y, and then we have some kind of relation between x, y, and y prime. Before we even start, this is pretty bad notation, but we'll get to that later. It's obviously mainstream mathematical notation. But an example of that could be, we want to maximize, y square root of y prime x as the function. So what we're going to do, find the mainstream proof here, is we suppose y is the extremum and consider some perturbation, y to y plus epsilon, and then eta, where eta of x, function of x, is some kind of function with eta alpha plus eta beta is 0, and epsilon is a real number, and some small positive constant. Then we know f of y plus epsilon n is alpha beta f of x y plus epsilon eta y plus epsilon eta prime dx. And then we're going to expand as a Taylor series. I know so many mainstream math stuff, but we're going to expand as a Taylor series, and we get f of y plus epsilon eta is f of y plus epsilon alpha beta partial f and partial y eta plus partial f and partial y prime eta prime dx plus some of this order epsilon squared. Again, I apologize for that. We're going to make this recurse in a minute with the new calculus. Note at the extremum, we've got epsilon equals 0, because we're at the extremum, right? So we have df on d epsilon equals 0. So therefore we will find that alpha beta df on dy eta plus df on dy prime eta prime dx 0. Now we're going to integrate by parts on that, and I'll spare you with details, but we get that integral from alpha beta df on dy eta minus d on dx df on dy prime eta dx, and then plus some value terms that we're going to vanish, right, to 0. And now we're going to use this thing, and it's called in the mainstream the fundamental lemma of calculus of variations, but in reality it's literally just an obvious geometric fact. I can make a video on that if you want, but it's literally so obvious. We don't even need to prove it without like anything other than geometry. I don't know why mainstream mathematicians and sense on, but that's what they do. And by the fundamental lemma, we're just common sense. We get df on dy minus on dx, df on dy prime, 0, which is the Euler-Lagrange or the John Gabriel equation. So now I'm going to show you how to make this better. So first of all, well, this is all kind of a bit nonsense. We're just coming up with this out completely nowhere, and it's not a well-formed concept. Like we're sending y to y plus epsilon n. This is just obviously a contradiction. This is ridiculous because we know. And we got real numbers. This should be fractional numbers. I would not refer to this as set, so you get infinite sets. That's rubbish. But essentially, this epsilon, you might recognize this here. It kind of looks like f of x plus h minus f of x equals h times f prime of x, right? Which, if you rearrange that, that's just the mainstream math, the derivative. So the correct version here, the actual version we want to do, is going to be the new calculus, where we want this eta to become m, and then we want to have, instead of here, y minus, my apologies, the eta was fine, the epsilon was wrong. We need m and minus n and eta, and then this is the m plus n. Now this looks a bit more like the new calculus derivative, right? F of something plus n minus n of x minus n over n plus n. And then this we know what to do. This order x epsilon square thing here. This is just the auxiliary function q discovered by the great John Gabriel. So then we set n equals m equals 0, and we know that q equals 0, and then that actually gets, this becomes m plus n equals 0. This is a little bit of mainstream rubbish here, and then we get to this. This integration by parts is in fact valid, and then as I mentioned, this is just geometric common sense. This doesn't need some weird analysis which is made up of its mainstream, real numbers, all of that. And this is basically how you do it. So that's the proof of the Euler-Lagrange or the John Gabriel equations.